Alright, so today we're continuing on our talk of Lie groups, finally. And so we're going to start out where we kind of abruptly left off last time in giving a bunch of examples of how to construct of various common constructible examples of Lie groups. And so our second case here, our second example, is going to be induced Lie groups, I guess I'll call it analytic groups here. I'm usually using the term Lie groups instead of analytic groups when it comes up, but I can switch between the two. Let G be a Lie group, H a topological group, and I.si from H to G a continuous homomorphism. Suppose that the pair H iota satisfies we saw a set of conditions a long time ago, probably a few days ago, really, called IM, which is going to make H a manifold with its induced structure. Then H is a Lie group. So we're going to let phi of G and phi of H be multiplication in G and H respectively. Then we have a commutative diagram from H times H. We can either multiply this in H to give us an element of H, or we can send this by two copies of our morphism to G, and then multiply it in G. And the idea here is this whole thing is going to commute. Which is going to make, going from H times H to G by implying G multiplication on iota times iota is a morphism. So phi H is a morphism as our iota is definitionally an immersion. And which makes H a Lie group. And we note remarks here. So we only need to verify that our pair of H with iota satisfies our conditions at the identity in H. suppose it does, and suppose we have an element H in H, an element G, and G being the image of H under our I, under our immersion. We're going to then define phi to be left multiplication in H by the inverse of our chosen element H. And we're going to let C be the map from G to G, as right multiplication in G by G times Y. Then we know that phi of H is going to be the identity on H, C is the identity on G, it's going to be G, and that iota is going to be phi of iota of C. Since G is the image of H, it's going to invert with itself and cancel out as G. And since C is an analytic isomorphism, and our injection satisfies our conditions at the identity in H by assumption, C on I must satisfy our conditions at the identity in H. Since phi is a homeomorphism, iota satisfies our conditions at H. And so we can do that for any point H, so it satisfies our conditions everywhere. We also need, it's also worth noting that we know that H iota satisfies our condition when iota is a local homeomorphism, if our map here is also surjective over we're doing it over a base field of the reals or the complex numbers. H is a covering, you say H is a covering group of G. Alright, and so that's our second example. Third, we should also look at submanifolds in the context of Lie groups here. So suppose G is a Lie group with a subgroup with, I'll write it like this. We have a subset H which is simultaneously a subgroup and a submanifold. Then H is a Lie group in and of itself. And this is actually by our previous unit, previous section. With our I being from H to G being an inclusion, and so is obviously going to be a continuous homomorphism and an immersion. We say in this context H is a group submanifold of G. If H is a subgroup submanifold of G, H is closed in G, as a submanifold we know is locally closed in its manifold in its parent manifold, that is, and a locally closed subgroup of a topological group is closed. Alright. And now, finally, we're going to be looking at group chunks. It's going to be our next actual section. So, a topological group chunk is a topological space X with a distinguished element E in X, an open neighborhood U of E in X, and a pair of maps phi, we send two elements of U into X, and C, which sends an element of U into an element of U, such that, okay, first off, for a neighborhood V1 of E and U, X being in V1 gives that we need a new page. X being in V1 gives that X is phi of X comma E is phi of E comma X. Secondly, for some neighborhood v2 of E in U, x in v2 gives that our distinguished E is phi of x and cx and phi of cx and x. You could probably tell kind of what the idea here is. And finally, for some neighborhood v3 of E in U, phi of v3 times v3 being contained within U let's write this on a new line. Phi of any two elements of v3 is in U, and for x, y, and z in v3, phi of x with phi of y and z is phi of x and y and z. And we say we have a strict group chunk if these equations hold whenever both sides are defined. Sorry, my voice went a little weird there. Are defined. We can turn a group chunk into a strict group chunk by shrinking our open neighborhood U. And we're going to write phi of x and y to be xy, and c of x to be, that looks like another phi, of x to be x inverse, whenever possible, whenever it is unambiguous. So, phone's buzzing. Let x and y be group chunks. A local homomorphism f from x to y is the local homomorphism f from x to y is defined to be a continuous map f from u to y, where u is a neighborhood of e to the x, such that f of e to the x is e to the y, f of xy is f of x, fy in a neighborhood of e to the x. local homomorphisms f and f prime from x to y are said to be equivalent if they agree in some neighborhood of e to the x. Group chunks x and y are said to be equivalent, are defined to be equivalent if there exists local homomorphisms f from x to y and g from y to x such that f composed with g is equivalent to the identity on y, and g on f is the identity on x. And we have analogous, spelled that wrong, definitions in the analytic case by requiring all spaces to be manifolds and all maps to be morphisms. So we have an example here. Let G be a topological group and let X be an open neighborhood of E with the obvious group chunk structure. X is a group chunk which is equivalent to a topological group. And so we can look at how to expand this kind of idea here. So we get the question, is every group chunk equivalent to a topological group? For finite dimensional analytic group chunks, they are. For metrizable locally compact group chunks, they are. For analytic group chunks modeled on Banach spaces? The answer is no. So it depends on kind of what conditions you have, whether or not you can assume a group chunk is equivalent to a topological group. Alright. Let's do one more section for the day. This is going to be on prolongation of subgroup chunks. So, let G be a topological group with a subset X containing our identity. Then X is said to be a subgroup chunk of G if there exists a neighborhood U of E in X such that X and Y in U gives XY being in in X, and our inverse also being in X. Now, suppose X is a subgroup chunk of G. We want to define a subgroup N of G as follows. N is going to be a set of G and G where there exists an open neighborhood U of E in G such that the intersection of U and X is the same as the intersection of U and the conjugate of X by G. So essentially it's the set of elements in G where we can find an open neighborhood whose intersection with X is kind of looks normal, essentially. Then we have, of course, N being a subgroup. We also have that there exists a neighborhood U of E in X such that U is contained within N. Let I from N to G be the inclusion. Then that brings us to a theorem where we're going to let F be U intersecting N, where a set of U intersects N, where U is a neighborhood of E and X. First off, f satisfies the axioms for being a filter base of neighborhoods of E and N compatible with the group structure. And secondly, suppose N is given the topology defined in F. Then I is continuous and gives an equivalence of the group chunks N and X. Well, let's look at our proof. First, we're going to suppose, for part 1, suppose all neighborhoods U of E and X are contained in N. Then first off, we need for U in F, there exists a V in F such that the product of V is contained within U. For U in F, there exists a V in F such that U contains the inverse of the elements of V. For U in F and G in N, there exists a V in F such that V is contained within the conjugate of U by G. And these are all pretty straightforward. A and B are just by continuity of multiplication and inverse respectively. And C is by definition of N. Secondly, by definition of the topology in N, I is a local homeomorphism of a neighborhood of E and N onto a neighborhood of E in X. As I is continuous as a map from N to G at E, it is continuous everywhere. And from this theorem, we see every subgroup chunk, whoops, yeah, that happens, is equivalent to a topological group. And it is worth noting, I is in general not a homeomorphism. Of n onto its image. If X is E, n is G with the discrete topology. Next, we're going to suppose G is a Lie group and X is an analytic subgroup chunk of G. Then, since n is locally homeomorphic, to X at E sub n, and X is a submanifold of G, our pair of n and our I satisfies conditions IM at the n identity in n, and so satisfies them everywhere, as we saw. We can then give n the unique structure such that, of an analytic group that is, of a Lie group such that I is an analytic group homomorphism and an immersion. With n and x locally equivalent then. As analytic group chunks. Now, next, let's look at the case where K is real or complex. Then n must be locally connected so that the connected component H of En in N is a both closed and open group manifold group submanifold, that is, of N. We call H the analytic group the Lie group generated by X. Now, suppose that I of H is closed in G. Then I is, actually this should be a new paragraph. It should be separate from our previous discussion. Suppose I of H is closed in G. Then I is a homeomorphism. So that H is in fact a group submanifold of G. Well, we know IH is closed in G, and so is therefore a Baire space. And H is locally compact and is connected. So is a denumerable union of compact sets. So we get the rest of this from a couple lemmas. First off, we get this from a lemma where we're going to let A and B be topological groups such that, well, first off, A is locally compact and a denumerable union of compact sets. Two, B is a Baire space. And third, we have map I from A to B be a continuous bijective homomorphism. Then I is a homeomorphism. This comes directly from a second lemma, which is automatic for the most part, which we're going to just write out explicitly. So we have a few setup conditions. One, A needs to be a locally compact topological group. Being a denumerable union of compact sets. Secondly, B is a Baire space And third and finally, we have phi from A times B to B be a continuous transitive operation of the group A on B. With this setup, then for any B in B, phi induces a homeomorphism of A over the stabilizer of B onto B, with n of B, of course, being the stabilizer of B, being the set of x in A, where phi of x in B is B. And so that will call it here for a chapter. Up next, we're going to look at homogeneous spaces and orbits, and then maybe formal groups. It's going to be a long video, I'm thinking, coming up. But that's it for this one. Thank you for watching.